Okay guys, first single phase and three phase circuit, equivalent circuit is actually the same construction. We have the magnetizing circuit and then the rotor circuit. So R1 and JX1 is referring to the stator, meanwhile JX2, JX, this is magnetizing, this is stator, so this is the rotor part. Okay, when we come to the single phase construction, we have to separate by the forward and the reverse magnetic field effects. So we have in the single phase we have two poles, which is of the upper pole and the lower poles. So the forward will be separated to the reverse one, and when we separate it, the both values will be half for the forward and half for the reverse. And it was stated that the single phase equivalent circuit are similar to the three phase, except that both forward and reverse component of power and torque which it present is indicated in the circuit. So we separate the rotor parts into forward and reverse. So when we calculate in terms of how much the current that flows through our stator input from the source, so we have to include the forward and reverse effect or values in terms of the impedance as well. So we shall calculate the Thevenin equivalent impedance of the elements. So when we want to analyze, we can separate, let's say we are taking this forward parts. So we shall replace the circuit with the Thevenin equivalent circuit, a series combination of RF and JXF here, to represent the forward equivalent field elements. So we can see here the RF must consume the same power from the given current as the rotor do, as the R2 over S would. And so the current that flows through the JX2 here and R2 over S here is at the same amount. So when we want to calculate the current that flows into the circuit, and we have to calculate the impedance of the forward and also the backwards. So the impedance of the forward equivalent circuit is equal to RF plus JXF. So this is the forward circuit. Meanwhile, the backward impedance is RB backward plus JXB. So this is the backward one. So we combine both together. So we apply the series and parallel calculation here. JX2 plus, this is in series, this one in parallel. So we have the equation like what you have learned in the circuit theory before. Ki is equal to V over impedance. And V, the voltage across the whole circuit here, divided by the impedance, total of forward and reverse combined, R1 JX1 plus the forward and reverse element. So R1 plus JX1 plus the element of your Thevenin impedance, Thevenin equivalent circuit or impedance of the forward and reverse. And so you shall have your stator current. Okay, we shall see the proper equation and calculation in the exercise to follow. Okay, in terms of their power flow diagram, this is the power flow diagram of your previous three-phase system. Meanwhile, this is your single-phase induction motor power flow diagram. So we can see that the core loss is moved to the right side of the diagram. So we have only this part, which is stator copper loss, rotor copper loss, and all the other loss is included into the rotational losses, the mechanical losses, core loss, stray loss on the right hand side. So okay, to further analyze the circuit in terms of their power factor, this is the same. Power factor equal to cos theta of the voltage versus current that flows into the circuit. And the input power factor, we have only single phase, one phase, so P in equal to voltage terminal times your input current and times the cos theta of your system. Meanwhile, your P out is equal to P converted and minus P rotational. So your P out is equal to P converted here minus the R rotor copper loss, and your PA gap is equal to P in minus stator copper loss. Or as we can see, or we can take the P out is equal to the converted power, whatever that we have from the output of the system, minus all the losses and the output power, the converted power here minus all the losses here, stray loss, core loss, mechanical loss, or the rotational loss. So we have the P out. And efficiency of the motor is equal to P out divided by P in times 100%. P out divided by P in, whatever we have at the output divided by input power, so times 100%. So in terms of air gap power, if we calculate based on the stator current, so I primary or I stator squared times 0.5 R forward, and the air gap in terms of backward is I squared times 0.5 R backward. So here we have here reverse and forward. The total air gap in the single phase induction motor is equal to both air gap power of forward and backward. Sorry, minus, and because this is the reverse one, backward. So the forward minus reverse. So in terms of induced torque, so if you at the air gap, we can calculate as P air gap minus or over synchronous speed. So at this air gap, so the speed is synchronous speed. At the converter, the speed is the mechanical speed of your shaft. So the load torque is equal to P out over mechanical speed and shaft speed. So this is the torque at load, torque at induced at the air gap. Meanwhile, the rotor copper loss is equal to P RCL of forward minus the P RCL backward as well. And this is the forward and reverse copper loss. We can calculate by the speed value times P air gap forward, and the backward speed value times P air gap of backward. So we can exercise this in the question to come. And the converted power is equal to induced torque times omega m mechanical speed converted, also can be calculated by the 1 minus S times omega synchronous. So P converted is equal to 1 minus S times P air gap. So this is almost the same like the three-phase motor. So this is a question that we shall discuss in the coming slide. So please perform the exercise first. So we shall discuss in the next slide to come.